meeting.
Okay, thank you.
Okay.
I will share my screen.
Yeah.
I think you should.
Yeah, just a minute.
Let me do. Okay.
Yeah. Now you can share your screen, sir.
Okay, cool. Could you see my screen?
Yes, sir. Yeah, we can see.
Okay, my name is Kazım Adavi. I'm a PhD student in Polytechnic Montreal in chemical engineering, and I'm working on CFD and working on nanomaterial synthesis. And in this session, we are going to just talk about reactor modeling using COMSOL multiphysics software. But before that, I'm just going to give you a brief description about CFD and different softwares that we can use in this field. CFD, as you know, is an abbreviation for computational fluid dynamic, and it can be used to investigate the behavior of the fluid for different purposes, and different softwares and methods developed for calculation of CFD systems. The point is, when you are using CFD systems, you have some equations that we know as transfer phenomena equation that included the momentum equation, the mass transfer equation, heat transfer equations, and sometimes you add more equation to this equation, such as Maxwell equation, and you solve all this equation all together to calculate the profile of your dependent variables. But how you can solve this equation, since sometimes you are dealing with finite differential equation that they are difficult to solve analytically, so you are going to solve them numerically. Different methods proposed for solve equations numerically. Finite difference method, it's the first and simplest way for solving a partial equation. This method just discretize the reaction, does discretize the elements of the equation analytically, and it cannot be used for complex systems. For example, when you are, based on my experience, when you are working with a system that you have heat transfer and fluid flow and mass transfer, it's difficult for just using finite different method. If I wanted to just where I can find my pen, okay. The second thing is that different softwares that we can be used in this regard. So I told you that we can use finite difference. There's another method, it's using finite element method. That software that they use for, can be used for finite element method are including like COMSOL. It's a good example. This method is much more stable numerically. So when you wanted to solve your equations using finite difference, I mean just separating that like dt per d time equal to ti plus 1 minus ti per just delta t. It's a finite difference. But in finite element, you use integral in different sides of your partial equation, and you solve those integrals on a specific volume that we call them element. And the finite volume is the same approach, but the difference is that when you use finite volume method, you have more stable equations. Fluent, ANSYS Fluent is one example of finite element. So as I said, different software that they can be used for the sake of CFD simulations, we can say the most famous ones. That the first one is COMSOL Multiphysics, ANSYS and OpenFOAM and Abacus. Each one of them has its own advantages and disadvantages. For case of COMSOL Multiphysics, since it brings about a lot of interfaces that they can be coupled and connected to each other, it's very helpful for most of field of studies, including engineers, I don't know, scientists, such as people who work on physics basics like plasma, like I don't know, light and electromagnetic behavior. ANSYS follow-on, especially follow-on, is a little bit the risk lower. It's more difficult to simulate. For example, for the case of reactors simulation that we are talking about, if you have simulated reactor, it's much easier than simulate your reactor using COMSOL Multiphysics. When you are going to use ANSYS follow-on, it would be some difficulties that you should define your reactions using UDF and then define them in your system. But the interface of COMSOL Multiphysics is so easy for reaction modeling and simulation. We said that for reactor modeling, COMSOL Multiphysics is a good choice, but another thing is that how many type of reactors we have. We can have packed bed reactor that is so usual in industrial sectors, that they just put the catalyst inside the reactor bed, and then they pass the reactants and the reaction boom will happen. The second type is fluidized bed reactors. This type of reactors bring about a high mass transfer and heat transfer coefficient that is helping to overcome. That is helpful for overcome the problem of mass transfer resistance and heat transfer and uniformity that we may have in your reactors. And it's much easier for handling. But we should know and be aware about the hydrodynamic of these type of reactors. For the next type of reactors, it's a moving bed reactor that you can use a kind of moving bed that can move along of your reactor. But the problem of moving bed is that you can have dead zones. And easiest reactor that I can say, and it was better to put it in the first, was that ideal reactor. So as you know, we have batch reactors, CSCR reactor, and PFR reactors. These reactors are ideal type of reactors that sometimes is, most of the time, is difficult to reach in reality. And all reactors that we have, including CSTR, PFR, all reactors that we have, including packed bed, fluidized bed, and moving bed, there are mimicking somehow the behavior of the reactions and reactors in CSTR and PFR modes. If I wanted to give you an example, for example, if your if your reactor is going to be more plug, it means that that you are going to just being closer to PFR type reactor. But when your reactor is just a mixer, you have a mixer and you have reaction inside, we can say your behavior is similar to CSCR. But the reality, for example, in case of this example, you have a packed bed reactor, the catalyst is loaded inside, and you have your inflow, the gas passes through the reactor, and not only your gases is moving, you have an axial dispersion also. So because of the presence of axial dispersion, your system is not a packed bed reactor, and you are somehow the problem of back mixing that is make your system similar to CSTR. So my question is, when is better to use CSTR? When is better to use PFR? When I say just CSTR, you can just assume we have a mixer, a tank with a mixer. It is closer to CSTR, or a fluidized bed reactor that is operating under homogeneous fluidization regime or bubbling fluidization regime. When you have a fluidized bed that is operating under fluidization regime, you have a lot of mixing, and it's much more similar to CSTR behavior. But when you are increasing your velocity, and your regime is going to be similar to, for example, fast fluidization regime, or or I don't know, turbulent regime, you can see that increasing the velocity, superficial velocity in the fluidized bed reactor would help you to your reactor behave much more like a plug flow reactor. So when you use which type of reactor, it depends on your kinetic. So when you are using CSTR, you have good mixing, but when you have PFR, you don't have axial dispersion, and when your reaction is happened, you can keep your concentration of reactants as high as possible. So if your reaction order is positive, it's more than 0, it's better to use PFR reactors, since you can keep the concentration of your reactant in the inlet as high as you can, and it's very helpful to reach to higher conversion. So for the sake of the COMSOL multiphysics, for simulation of the reactor, you should solve some equations. The most well-known equation for solving behavior of the fluid is Navier-Stokes equation. That is formed of, for example, you should solve continuity equation and also momentum equation that include viscous terms and also inertial terms, and also you have external force that can be exerted on your fluid system. It's a very good point that you take care of, since a lot of people today are working on I don't know, behavior of nanoparticles fluid inside some reactors, and what is the effect of electromagnetic wave, that these forces can be any type of external forces that can be applied on your system, and you should solve this equation to calculate a dependent variable that we call it here velocity. For solving this equation, we need some set of boundary conditions. For boundary conditions, as you know, each boundary that you draw in COMSOL, you should have a boundary condition, and assume you have these walls, and this wall is just there is no slip boundary condition. That is a common type of boundary condition for walls of the reactor. And it means that the velocity of the fluid exactly near to this layer is similar to the solid velocity, and it's equal to 0. And we can apply that in the walls, and we have an inlet and we have an outlet. And for inlet and outlet, For inlet and outlet, we can define for inlet, we can define the velocity of fluid, or we can define flow rate. In the outlet, we can just define pressure of your system in the outlet of your reactor, since most of the time your fluid is going to be released in the environment or downstream units. It depends. You can define downstream units here, pressure here. For example, if it is releasing in the environment, you can define partial pressure equal to 0 in the outlet. So here is the reaction that it's the equation that you use when you are going to solve the velocity. When you are dealing with free domains, there is no catalyst. Maybe you can load your catalyst, I don't know, on the walls. It depends on your work. But for the case that you have, for example, packed bed, and you have your catalyst or one of your solid elements loaded inside the reactor, what should we do for calculation of velocity? We go through Brinkman equation. Brinkman equation is an equation that can be used for calculation of the velocity in porous-medial domains. It's a more general than Darcy equation. Darcy equation is an equation that can be used for calculation of velocity when your porosity is so small. It's maybe less than 10%. But for case of the Brinkman equation, it can be used for example, for fixed bed reactors that the range of void fraction can change. I don't know, let's say around 20%, 25%, or 30% to 60%. It depends on shape of the catalyst. For example, in hydrodesulfurization plants, I know that the void fraction is somehow around 30%, and for case of reforming plant is around 50%. And you can define and consider the bed of the catalyst as a porous media and solve those equations. Someone may ask me, okay, why we are not considering particles separately and then solve equations for that? The question is, when you are defined, you have a real bed, you load a lot of particles inside, and these particles, if you wanted to solve them individually, you should define boundary condition on the surface of each of them as no slip, and it loads a lot of computational cost, and it's not easy to solve. So it's a way that we can solve our fixed bed as a porous media, and we can reach the velocity profile that we want, not just velocity profile and pressure, everything that is related to our system, related to velocity. Another equation that can be used for calculation of parameters that we are looking for inside a reactor is energy equation. Let's say we have a particle placed in a tube, and it is heating in a constant temperature. The walls kept at 600 Kelvin. And also you can see there is a gas flow that is moving up. For case of this example, we solve the Navier-Stokes equation and no slip boundary condition on these walls, and no slip boundary condition on surface of your particle, and the flow is moving up, and temperature is penetrating inside of your system, and you use this equation to calculate the temperature. It's energy balance in your system, and you consider the term of convection, since we have velocity here and our fluid is moving, so we should consider the velocity here, and this velocity helps to improve the heat transfer. And here we have the conduction behavior, and here we can have heat generation sources if we have, for example, for the case of, I don't know, microwave heating, I don't know, for the case of induction heating, for the case of reaction that you have, a heating is happening inside of your particle because of, for example, reaction. So you can define the heat of the reaction that is generating inside of your particles using corresponding equations such as the rate of the reaction that multiplied with delta H of the reaction. So here you can see an example that could both heat transfer and fluid flow for a single particle that placed. This single particle can be a catalyst. So you are investigating the behavior of that single particle in your system, and you apply the fluid flow and heat transfer. One example that we performed already, I just wanted to give you explanation about what type of reactors can be simulated inside the fluidized bed reactors. It's a reformer reactor, reformer tube. As you know, reformers, methane reformers are type of reactor that they are using for production of hydrogen. The feedstock is typically methane, water, and carbon monoxide. It depends on type of the reactor, but it's typically these three gases that they pass through a bed. This bed has different regions. First region is for increasing temperature. There is an inert catalyst here, just to increase temperature, so to a specific temperature such as 650, to prevent undesired secondary reaction such as Woodward. So we have feed gas here, that is temperature is like 500 degrees C. In this length, we increase the temperature to, let's say, around 650. And then you have your second type of catalyst that has lower activity, that known as, I don't know, semi-active catalyst. And this low activity is because we are going to have lower rate of the reaction here in this part, since the reaction is endothermic. Since reaction is endothermic, you are supplying heat with heat and walls. But if you consume heat in the center of your reactor, what would be the result? The temperature inside of the reactor, in the center of your reactor, would reduce. And when the temperature in the center of your reactor reduce, the problem would be started. Since you have lower temperature than 650, and you have the problem of Woodward. But in this section, you reduce the activity of catalyst with loading lower amount of, for example, nickel on the surface of your catalyst, or any type of catalyst that you are working with. In the third part of your reactor, you have high active catalyst that has a higher content of active site that can overcome the problem of lower and limitation of the previous sections. But for solving this type of reactors, that I can call it a good example and a complex example, we applied just Brinkman equation to solve the velocity profile inside the bed. And also we just added the heat transfer equation to investigate the temperature profile in the bed. And also we solved the mass transfer mass balance that we wanted to just calculate the composition of different elements. Here is the profile of the temperature and in the system radially, and you can see the temperature in the center of the reactor is lower than walls. Its the reason is because the reaction is endothermic, and we have like this type of temperature profile inside of our reactor. One interesting thing is that we can define and we can just simulate behavior of not only the bed, but we can define single particles and single pellets inside of our reactor, and we can investigate those particles separately. It is a catalyst, reforming catalyst that can be investigated in terms of mass transfer. In terms of, I don't know, some people do it with increasing investigation of tension, and you can see how mass and your reactant diffuse inside of your particles, and you can use these results to improve your knowledge about your system. Here is the problem that we have sometimes in our simulations. You are developing a catalyst. The catalyst has activity surface A, or porosity, I don't know, let's say 10% porosity inside of your catalyst. But the case and the important thing is that you should be careful that all of your reactant should be in touch with your active sites in inner sites. If they are not just reaching to inner parts, sorry, you are not going to have any reaction in your inner parts. So it's very important to investigate your particle in terms of mass transfer, that gases elements can penetrate inside of your pellet, and then you can have more reaction inside the reaction. But maybe in reality, in industrial sectors, you have just the reaction on the out surface of your catalyst. But it's the case that you can investigate in COMSOL multiphysics. You can define your catalyst, you have the fluid flow, you have compositions, and you can check when the reactant can penetrate and what is the best shape of optimum shape of the catalyst, and using that optimum shape for your further improvement. For case of the, for example, profile concentration, you can have profile concentration of your system using different method. Another method reactor that I modeled here is the methanol reactor. Methanol reactor is a methanol synthesis reaction is an exothermic reaction. So I talked about reforming reactor as an endothermic reaction, but what if we have exothermic reaction, such as methanol synthesis? I don't know how many of you heard about the methanol synthesis reactor, but the methanol synthesis reactor is generally a tubular type of reactors that they are placed inside kind of boiling water that can just remove produce heat during the reaction from the reactor. And it's very practical for being very practical for having more uniform temperature distribution in this type of reactors when we have just a bunch of tubes rather than a big reactor. We use a methanol reactor that is just one tube, and we simulated all results, and you can see that the concentration of different component is calculated based on the length of the reactor. It's very helpful that see what is the best size of the reactor, and even you can change the dimension of your reactor and see what is the different effect of, for example, reactor diameter, reactor length on the concentration of your final product. For example, you may ask, okay, it's not a big difference between this length and this length, so we can just have, I don't know, 5 meter length reactor tube. That's enough. It depends. It's very helpful for help you to scale up of your system. You are developing a new system, a new reactor, and you need to scale up that. What is the procedure of the scale up? You should just jump inside the building your pilot scale or industrial scale, and then, okay, it doesn't work and I just wasted a lot of money. No, you should just do all simulations, all investigations, and do that. When you did your simulations, you may raise some question. Okay, let's say I face some uncertainties, and it's better to know them better, so you can do that in lab scale, and then you just backing again to industrial scale and solving these uncertainties by this way. Here is the temperature profile in methanol reactor. That is a peak here. It's a very good point that the reason that is we have this type of temperature profile along of the methanol reactor is that we have exothermic reaction, and in a specific length of our reactor, we reach to maximum rate of reaction in maximum heat generation. So we have a peak here. After this length, the rate of reaction going to be decreased, but this peak is related to the reaction rate in a specific length of the reactor. So my question is, when you are going to work on a reaction system, and it is the reaction is exothermic, you are not going to just increasing temperature. You cannot decrease temperature to lower than a specific temperature. For example, for methanol reactor, the temperature, operating temperature is around 250. But what if I work under, I don't know, 400? You will have the problem of thermodynamic. What if I work with, I don't know, 150? You have the problem of the kinetic. Since when the temperature is lower than, I don't know, this value, 250, let's say in average, or 260, you can see that the kinetic is not as strong enough to perceive your reaction. And when you are increasing temperature, you are, since the reaction is exothermic, high temperature is not favorable. So you are going to have lower yield of methanol in your outlet of your reactor. So it would be another problem. Another example, an application of COMSOL multiphysics. So I just told you about an endothermic reaction that you need to supply heat. And it is a reforming reactor. We define an exothermic reaction that we need to just remove heat from the reaction domain and in the fixed bed reactor. But you may ask me, okay, what about fluidized bed reactor? You can do your simulation in fluidized bed reactor. It's a little bit difficult. Sometimes it depends on your system, but it's now it's, I think, based on new modules and new module of COMSOL that they developed. You can simulate fluidized bed reactors easily, and you can couple it with mass transfer. But in terms of simulating of fluidized bed reactor, that is mostly based on two-fluid model that consider both solid and particles as fluid. You can simulate just this method, and it's a little bit computationally costly compared to fixed bed reactor simulation. But the procedure is the same. So today, some people like to do all of the reactions in fluidized bed reactor, and it's the opportunity that you have to model your system not only in a fixed bed reactor but also in fluidized bed reactors. Another example that I'm going to give you is the design of your reactor. Sometimes some people is facing some problems, such as they have attrition in their catalyst, they have attrition in a specific type of a specific location of their bed, and this attrition cause some issues, some problems on the surface of the catalyst, since it can, for example, it's a desulfurization reactor, and the gas contains H2S, passes through some adsorbent, and this adsorbent can absorb the dangerous H2S that is dangerous for downstreams catalyst. It can deactivate catalyst easily, so we need to remove that. The reactants go and pass through the bed, and after passing through the bed, they would be adsorbed by adsorbent, and it's how it works. But the problem sometimes is that when we have this distributor, the gas coming down and touching the surface of the bed, there is attrition here, and this attrition causes some pressure, such a problem such as clogging the bed, and your pressure drop inside the fuel reactor increase so fast, and you should take care of this issue. Otherwise, you should unload off your catalyst. It's an example, for example, we did for the design of this type of reactor and investigating what is the effect of this different type of distributor. You should take care of the mesh size that you are considering. You need to do mesh independency analysis to be sure that there is no effect of mesh size on your simulation anymore. Otherwise, you are just doing a simulation. You may have some errors, but how you can optimize that error, you can decrease the size and see when the results are not going to change, and it is the best location that you can have. Another problem is the problem of channeling that maybe you have in your system. It's an animation of that reactor that you can see that in the center of the reactor you have some type of channeling, since this adsorbent is going to be consumed, and after finishing that you need to just unload that and loading fresh catalyst and adsorbent. But when you are facing channeling, the problem is that you are not having all reaction in all domains, central domains of your system, and then you are losing and wasting a lot of money and your time. So these two examples are very good examples that you can apply for reactor modeling that can detect the behavior of your fluid. It's very interesting that I tell you that the basic approach that we consider in this simulation is like considering a tracer. Most of you know that what is RTD analysis. RTD is study the resistance time distribution inside of your reactor, and when you are doing RTD analysis. You are investigating the profile of the behavior of and hydrodynamic of your bed, and see what is the residence type of different components inside of your catalyst. Since when you are going to do your simulation, in each type of reactor that you are dealing with, you need to know what is the distribution, what is the residence time of your reactants in your reactor. This residence time is very helpful to give you this idea that what would be your conversion finally. So here we injected a specific concentration of a reactant, and that specific concentration just passes through the bed and the reaction or adsorption happening, and then it's going to be consumed. And in this level that it's finished, you need to just disload your adsorbent. As I said, here is the problem of channeling. What is the problem? It's the distributor. For example, you can design your distributor in different shape. Okay, I'm going to solve the problem, how I can change the behavior of the fluid. But here you can see that if I design it in like adding some holes inside the bed and giving that a little bit curvature, it causes losing some side parts of the bed. And for this case that you have a smaller holes, maybe it works better since it's not going to let a lot of flow passing from the center of the bed. So it's another type of reactor. This is for adsorbent mostly. So I firstly just explain you how you can design a fixed bed reactor that your reaction is endothermic. Second, we defined an exothermic reaction, and here is an adsorbent that is going to react. But you may ask me, okay, you just defined a simple distributor. What if we have a much more complex system? I would say that we can do simulation for distributor separately. We can design any shape of any type of system that we have, and we just can go through the results. For the case of this system, the one point that I just want to mention again, you have different domains. That here is free. Here is the ceramic balls loaded for support of the bed, and here is the bed support. And you solve Navier Stokes in this domain since there is no catalyst. You solve Brinkman equation for this domain, and you solve mass transfer since you have tracer. And for the sake of this type of reactor, since we have inlet flow as in a temperature of your reactor that we needed, it's around 300 degrees C. We don't need to just add any external heat, and you can just say, okay, it's going to be somehow an adiabatic system, and no adding heat, not removing heat. But you are solving in the same time mass transfer equation and also fluid flow and diffusion, mass transfer diffusion and mass transfer convection, both coupled with fluid flow, since for the case of convection, you need to have the velocity of your fluid inside of your bed, and this velocity is going to be used for convection purposes. Yeah, there is a distributor. Another type of reactor that that can be simulated in COMSOL is a shift reactor. It's a shift. It's high temperature shift reactor. that just using for hydrogen purification. This reactor is the reaction is just a reaction of carbon monoxide with water, and then this produce hydrogen and carbon dioxide. This reaction is exothermic, and it can be reached to equilibrium point so fast compared to reforming, for example, reaction. In the case of reforming reaction, it's difficult to reach to equilibrium points, and you may reach to, I don't know, in industrial scales, you reach to the percentage like 1% of methane as a slip methane inside is outside of your reactor, and it's I think the equilibrium is lower than this value, and it means that we are a little bit far from the equilibrium point. But for the sake of for the case of shift reactions, for this case of shift reactions, you just have a fast reaching point to equilibrium point. One example that we should say about reactor design is it's a very good example is shift reactor. In case of shift reactor, that syngas going to be inserted to the reactor. It's the volume metric of carbon monoxide will react with water, and it would be transferred to hydrogen, but we have thermodynamic limitation. Here we have a thermodynamic limitation, and the presence of the thermodynamic limitation pushes us to just applying, since we have high temperature, we have the problem of thermodynamic limitation, what we can do in this regard. And the answer is that when we are going to do this type of reactors that we cannot reach highest conversion in the reactor, we do that in multi-stage type of reactors, that we decrease temperature gradually and see how we can increase the reactor. So for the case of shift reaction, we have a high temperature shift reaction that reduce the amount of carbon monoxide in the inlet, and reduce that to something around 3%, for example, 30% in the inlet, let's say 30% in the outlet, but it's the limitation of thermodynamic. We cannot reduce that anymore. But how we can reduce the amount of 3% in the outlet? We define a lower temperature reactor. Since it's, if you draw a conversion versus a temperature, you see this decrease. And if you decrease temperature, you have higher conversion in case of exothermic reactions. So you have a lower temperature reactor, that is low temperature shift reactor, that just eliminate the trace amount of, not trace, it's 3%, but when you add it to the low temperature shift, it would be around 0.1%. That is quite low, and you can see how you can overcome your system. We designed this type of reactor, and we designed an application, and we gave it to industrial partner, and it's now using for operating system, and they can predict what will happen in the reactor if they do apply a specific operation condition. Okay, we talked about COMSOL simulation, but what about Kinetic? Since when you are going to talk about reactor design, what is the most important thing? Is Kinetic. So we know what is heat transfer, we all know what is momentum balance, we know what is mass transfer, and so what is the rate of reaction? The most important thing that you could have a successful simulation, regardless of your reactor, is applying a right kinetic model. Developing a kinetic model, it's not so easy. You should take care of a lot of parameters. You may have catalytic reaction, you may have non-catalytic reaction. For example, for the case of reforming reaction and a methanol reaction, you have catalytic reactions. For the case of adsorbent that I showed you, it's kind of non-catalytic reaction that your catalyst is a reactant. And when you are going to develop your kinetic, I'm just going to introduce some equations about the kinetic of solid state reaction. And you can see that the kinetic is like, it has a general form like this. The alpha is the mass change of your catalyst, your reactant, your adsorbent, for example, that is defined like similar to a conversion. K0 is a pre-external fuel factor. That is the number of collision, based on collision theory, is number of collision that you have inside of your system. Is number of collision is a very good representative of that, how many molecules are contacting with your catalyst. But based on collision theory, if you wanted to have a reaction, your catalyst should have, your reactants should have enough energy and right orientation. So you define this term, that is the fraction of catalysts that they have enough energy to react with each other. F alpha is the reaction model for a non-catalytic system. And these terms, for the case of the reaction model, with preceding the reaction, we may face different behavior for our systems. So different reaction models developed already, I will explain them later, but that they can be used in this regard. And you can just use model fitting and see what is the best fitted model. But maybe you ask, okay, you are just saying just limited number of equations. What if I couldn't fix my model in case of non-catalytic? I would say, okay, you can develop your model, but there is a lot of another types of kinetic models that are proposed in the literature. Here is the effect of partial pressure. You can see how your reactants or products concentration may affect your system. Actually, this F alpha is somehow the concentration also, since alpha is convergent, and you are telling what is the effect of concentration of my solid. And if my conversion proceed, what will happen for my reaction? And here is the effect of partial pressure, since I'm talking about gas solid non-catalytic reactions here. Okay, these models can be mixed to each other and form a general form. For different type of reaction model that I just introduced you, is that the behavior is a little bit different. For example, for the case of power law equation, the power law models that they assume based on nucleation model. Based on nucleation model, when you have a reaction, it's similar to crystallization. Some crystals going to be appear in your system, and these crystals, these crystals are, we call that nuclei in the first time that they appear in your solution, and they start to grow. This growing cause accessing more active sites for other materials to reaching to this point and then reacting with your system. So your rate of reaction will increase after a while. So you are proceeding your reaction. With proceeding your reaction, rate is increasing. Why your rate is increasing? Since you have more active sites. You have more surface for reaction. But sometimes for it's not real, since maybe you lose some active sites when it is growing because of ingestion or coalescence. So you can say, okay, maybe Avram is good for me, but sometimes, okay, you say, I have a particle and it's difficult to diffuse inside internal part of my reactor. And what would be the result? I would say that, okay, your model is not going to follow power law equation anymore. So it's better to use diffusion models. That means that by pursuit of your reaction and your solid going to being penetrate inside of your catalyst, you will have the problem of diffusion, and it would limit your reaction rate. But sometimes your reaction rate is going to be limited by shrinking unreacted core model. The shrinking unreacted core model is based on this idea that when you are proceeding a reaction, it's not going to be limited by diffusion. It's going to be limited by the surface area of the reacted and unreacted system. So you have this percentage, and you know how much your catalyst your reaction proceeded. Okay, for the sake of developing a right kinetic model, you should take care of extracting intrinsic kinetic model. So what is intrinsic kinetic model? Intrinsic kinetic model is the reaction model that develop, and it is independent of bed hydrodynamic, dependent of mass transfer limitation, and independent heat transfer limitation, and you can use it for case of a scale-up. Here I have a question. I'm developing a kinetic inside lab, and I'm going to apply that inside COMSOL. Does it make sense? I'm scaling up our system, so I'm increasing the size of particle in the industrial sector. What would be the problem? The answer is that when you are doing this, when you are applying these changes, you should take care of your kinetic study. Your kinetic should be intrinsic, otherwise you cannot use it. It's limited to a specific condition. And it's very important that you know what is the rate limiting a step of your system. If your reaction is limited by, I don't know, external mass transfer, if your reaction is limited by external mass transfer, you can say, okay, if I increase the velocity, my reaction is my reaction rate going to be increased. Here is a curve that you can use based on your reaction rate and gas velocity and particle size. Increasing your gas velocity or decreasing your particle size will reduce, especially for the case of external mass transfer. As you know, if you have a catalyst, your reactants should reach on the surface of your catalyst. So the problem of external mass transfer can be reduced by velocity. So if you increase velocity and you see, okay, my reaction rate is increasing, it means that you have external mass transfer limitation. When you increase the velocity, there is no change. Okay, it's not mass transfer, external mass transfer limited anymore. If you decrease the size of your particle, you can overcome the internal mass transfer limitation, and then you can see when you can solve this issue. Since, as I said, if you wanted to have a reaction, your reactants should penetrate inside of your bed. Otherwise, you are losing some internal parts and your reaction rate is not a real reaction. When you lose this level, that there is no changing with changing velocity and particle size, it means that your reaction is just limited by reaction itself. And in this level, I can say that only temperature can affect your reaction model, reaction system. And then you can say that my reaction is intrinsic and it's not going to change. But sometimes you may ask me, okay, I'm going to work with an adsorbent with a specific particle size. What would be the problem? I have made some internal diffusion problem. What would be the result? I would say, okay, you can develop your kinetic based on your system, based on your real particle size, and call it apparent activation energy or extrinsic activation energy, and using those kinetic parameters for your modeling purposes. And if I ask me, I would say applying a right kinetic to your reactor modeling is the most important part of your simulation procedure. Otherwise, you will not have right results. I think 1 hour is over, isn't it? Could you hear me? Hello? Can someone just confirm that? Okay, it seems that we reached to around, I don't know, since time difference, I need to check the time, sorry. So we have something around 45 minutes. I'm in these 45 minutes, I will go through COMSOL multiphysics software. So I'm just going to ask you if there is any question and any point so far. No question? Okay. I will go through COMSOL multiphysics software, but sorry, I'm not sure that I'm audible. Can someone just confirm?
Yes, sir. Yes.
Okay, cool. So here is COMSOL multiphysics software. I don't know how many of you have this software in your system. So you can use, you can double click on icon of the COMSOL, and I know all of you know that when you have your system, your window is opening, the first page that you have is this page, this window. The first one is model wizard, and the second one is blank model. What is, for case of model wizard, if you click on it, you go directly to what is the dimension. For the case of dimension, for the sake of dimension, you have 0 dimension, 1 dimension, 1 axis, 3 axis symmetric, 2D, 2D axis symmetric, and 3D. And someone may ask me, okay, what is 0 dimension? I would say that what is when you are simulating a ideal CSCR or ideal PFR, you have kind of no dimension. You are not considering dimension. You are just solving equations, and it's why you don't have any dimension. In 1D system is when you use it just when your reactor is concentrations are changing in 1 dimension. And in 2D and 3D, it depends on your system. If you just you can ignore the changing of your one independent variable in one specific direction, you can say, okay, I can use 2D or 3D. So okay, for case of 3D equations, 3D models and 2D models, the system is much higher computationally costly, and it is preferred that you use lower dimension, since you will have lower computational cost. But it's better to be sure there is not any big difference between higher dimension like 3D with lower dimension like 2D, and you should be sure that your assumption about your model is model geometry selection is right. After selection, for example, I select just 2D. You go to select your specific interface that you are going to work with. A good thing about COMSOL multiphysics is that you can just couple a lot of interfaces with each other and adding to your system. Since I'm going to work with, in this session, we're talking about reactors. And I don't know, I think most of you are chemical engineers or maybe mechanical engineers, isn't it?
Yes, sir. Just I want to notice you that screen is not visible, sir, now.
Okay, I'm sorry. Okay, cool. Sorry. Could you see my screen now?
Yeah, it is visible now.
Okay. So I just do the fast explanation. It's just selection of the dimension. Here you just select the physics and interface that okay. Here you can see how you can select physics that you are going to work with. Here is AC/DC. We may have different and a specific type of reactors that can be induction heating reactor, that can be plasma reactor, that can be microwave reactor, that can be residual heating reactors. So you can apply heat with using AC/DC current. You may have want to consider reaction and effect of acoustic waves and sonication inside of a reaction domain. So let's say, what is the acoustic? You can define acoustic modules here, coupling that with velocity and mass transfer and heat transfer, and see what is the results. For the case of chemical species transport, it's going to be used for mass transfer. For the case of electrochemistry, you use it for electrochemistry and designing fuel cells, corrosions, and things like that. For the case of fluid flow, you are going to investigate hydrodynamic of your bed. For heat transfer, you can calculate the heat transfer. For the case of the optic, it's I think it's not much related to reactor. Maybe you can say, okay, I have a photocatalytic, I don't know. For the case of the plasma, you can use plasma assisted reactions in your system. For case of radio frequency, also you can couple it with plasma similar way. And for the case of semiconductors, it's basically for electrical stuff, for structural mechanics, for doing and measuring tensions, and I don't know, physical things. And for the case of mathematics, you can solve partial differential equation based on defined boundary conditions. So for the case of reactor, you have different modules. If you open each of these interfaces, you can see some subsections, and some of them are used as coupled. For example, for case of reacting flow, if you select laminar flow that is reacting flow, it would couple your reaction system with your reaction system with your fluid flow, and your reaction, and you have the velocity profile coupled with mass transfer. And for the sake of, for example, fluid flow, you have a single phase flow that can be either creeping flow, laminar flow, turbulent, and any types of other types of catalyst. Other types of fluid flow. And here is the post-medial domain that can be helpful for selection of your preferred domain. Brinkman equation and free and post-medial domain mostly used for simulation of fixed bed reactor. Two-phase Darcy flow is good for simulation of behavior of gas and solid inside the two-phase system, considering mass transfer. In the case of non-isothermal, it's helpful for calculate the constant temperature profile inside of your reactor, considering fluid flow. So I'm just going to select a laminar flow. I add heat transfer in fluid. And I add just transport of diluted species. These three modules are the most common modules that usually can be used for simulation of velocity, temperature, and concentration. Another thing is that how I wanted to simulate my system. It can be either stationary or time dependent. Stationary is that your dependent variables are not going to change with time, but for time dependent, you will have the variable of time, and you can see what is happening by time. But for most of reactors is a stationary models for fixed bed reactors. For case of adsorbent and non-catalytic reaction, since your reaction is proceeding and your catalyst, I don't know, let's say your solid reactant is going to react, it's changing by time. So you should use time-dependent module in this situation. So in this case, I just select stationary. Okay, here is the COMSOL multiphysics window. Here is model builder, settings, graphic, and its toolbar. In this section, you define all of your boundary condition, you add all of your numbers, parameters, variables. In this settings, you can apply changes in a specific area. Here you can see the results, and you can see the graphical interfaces. Here you can see numerical results or even some messages, and processes that are happening inside of the software. Okay, I just go through geometry. I select a rectangle. I want to just define a tubular reactor. And I'm going to define the sizes based on centimeter. And define the widths are like 0.1 and height of 0.5. It's a kind of, it can be a kind of tubular reactor. And I add just I just can go through materials to select a specific chemical, a specific material to my system. And I just going to add, I don't know, let's say we can add, for example, water here. Here is the properties of the material that I added, and these tick marks show that which properties are using for the case of this simulation. So, for example, for bulk viscosity, for electrical conductivity, for speed of sound, we are not going to use these parameters, so they are useless. But just we are using dynamic velocity, viscosity, specific heat and heat capacity, density, and thermal conductivity, and they are function of temperature. You can change them everywhere that you want. You can put your function here, or either you can just define a constant. But I just define the water here. Here I defined the laminar flow. But I have a porous domain reactor. I can enable porous media domain. Here you can see Navier-Stokes equation. You see that here is inertial, and here is viscous term. Here is external force. But since I activated porous media, I right-click on laminar flow and I select fluid and matrix properties. And I select this domain as a porous media, and here you can see Brinkman equation that usually used for calculation of velocity in porous media domains. Okay, for this domain we defined that we defined the fluid properties based on water. For the case of porous domain, you should define two properties. That first one is porosity. Porosity can be a number from 0 to 1. Let's have 0.5. And permeability is the ability of materials to pass the fluid through themselves. We can just change it to this number. It's based on millidarcy or square meter, and you can measure it in the lab based on Darcy equation. It's a very easy way that you can calculate permeability. But the permeability is a function of your fluid behavior also. It's not just a property like porosity. It's a function of velocity of your inlet flow, type of flow, and it's very important, and also pressure drop of your bed. So secondly, I just go to select inlet. I have inlet like 0.01 meter per second, and here is walls. So far already that the boundary condition is 0, velocity is equal to 0, and I defined outlet. That pressure is equal to 0. That means that it's releasing to the ambient and its gauge pressure is equal to 0. So here is the modeling that we applied for porous domain. It's so easy, just inlet, outlet, walls, no slip, defining the fluid and porous media domain properties. Then we go through heat transfer. I have an inlet temperature, fluid condition, inflow. I can define the inlet temperature as ambient temperature, and I have outflow here. And it means that the value of the gradient of velocity in the outlet of the reactor is equal to it's equal to 0 in axial direction. So you have inflow, you have outflow, you have thermal isolation and walls, but it's not things that we want. We just define the temperature, constant temperature or walls. And I define just 800 degrees C. And just I select a specific media, porous media for case of selection. Here I have my fluid that I should couple it with velocity. And here is my porous media domain. Okay, you can consider that you can consider porous media, and you can define the fluid properties and porous media, porous matrix properties in this section. Why you need to define this stuff, since your properties are changing with porosity. You have a matrix that can be a catalyst, that can be a reactant, and it is solid. And its thermal properties is completely different from pure fluid. So defining this section help you to just reaching to calculate the average properties of your fluid and your solid. So, okay, let's just deactivate that, since we need to add some more data. For the case of mass transfer, you can define first your components. You may have a reaction here. Let's say A plus B give us C. So I add 3 components like A, B, C. And in the inlet of the reactor, you can define your concentration. So we have 1, and we define just 2, and it's 0 in the inlet of the reactor, and we have the outflow here. Also, we have no flux here; it's isolated completely. For the case of transport properties, it's important to mention that when you are going to deal with heat transfer, when you are going to deal with mass transfer, you should couple your velocity with these equations. So you can define, for example, velocity, and it can be coupled with this module exactly. I mesh my system. And then you can solve it. Any questions so far? Okay, when you're just starting your simulation, it takes time. You can see what is the progress of your simulation here. Here you can see the conversion of your system. This graph should be like this, and it should be reduced to a specific value that shows that your model is converging. Otherwise, it's not going to be converged. Here is the velocity profile. Near walls, you have velocity equal to 0. In the center, you have higher velocity. But you may ask me why it's look like that the velocity here is like somehow uniform. The reason is that based on Darcy investigations, when you have a porous media, when you lose somehow the radial change of your velocity. And the smaller the fluid fraction, the smaller variation of velocity in radial direction and axial direction, obviously. Here is the velocity profile that we have. It's exactly fit. It's because of the boundary condition is no slip, the velocity is 0. And here you can see the boundary layer of momentum. And this boundary layer is important to be applied for mass transfer purposes and heat transfer purposes. For the case of pressure drop, you have the contour of pressure drop, and you see that we have around 50 Pascal pressure drop inside of this bed. It's very small, but we have a still pressure drop here. Here you can use these results for estimation of pressure drop in industrial reactors. So when you are going to simulate your industrial reactor, you can just calculate pressure drop using software such as COMSOL Multifaces. Also, we can use Brinkman Equation without no simulation. And see what is the pressure drop. Here is the temperature profile. And you can see it reached to the temperature of the wall since it's stationary and there is no changing. And it's the concentration profile. But since we don't have any reaction, they are not changing. So for the case of the temperature, we have the inflow here. The temperature is this, and it's the temperature. And we didn't couple it. It's the reason that we didn't have a convection in temperature profile. If we compute it again, okay. It's the profile of temperature when we couple it with velocity, and you can see the effect of convection here easily. You see the lower temperature in the center of your reactor, higher temperature on walls. And then for the concentration, if you want to change your concentration, you need to define your reaction. In the reaction rate, you can just define your reaction rate here. What is the kinetic? You developed your kinetic based on different components. and you can see how it would change. For example, you can say just add your pre-exponential factor is like this, multiplied with exp minus 40 kilojoule per mole per R constant multiplied with T, temperature, multiplied with concentration of your components. Here you have Ca, Cb, and Cc, and Ca. When you have a red thing, that is a problem in your definition of your system, and it's now the problem of unit. When it is red, it's wrong totally, but when it is orange or yellow, it is the problem of most of the time. The problem of unit, and it's the unit of this pre-exponential factor is 1 per time, 1 per second, let's say. So it's consuming. I add this one here. I multiply that for B also, and multiply it for C, but it's positive. It's just an example. And here is the domain of reaction. Okay, it's the concentration profile that you can see it's reduced after the reaction, and it's following the temperature profile, since the higher temperature is stronger kinetic and higher reaction rate. So it's an example that can be used generally. It's so general, but I'm sure that there is a lot of details for different types of reactor that can be used for different purposes, for microreactors and fixed bed reactors and so on. So I think we have 15 minutes left. If there is any question about your works, about other which type of reactors we can simulate, limitations, I'm all ears. There is no question?
Participants are requested to ask a question. Otherwise, you can write in comment box. Digvijay sir, any question?
There is no question. I just left my email address if you want in the chat part. If anyone has any question later about simulation, you can feel free to email me.
Yes, definitely, sir. So if anybody is not having any question, we are about to finish this session. Before that, once again, I request that if you have any question, participants, they can ask or they can just text in the chat box. Okay. So now here we are towards the end of this session. Kazem sir has explained in very good manner that how the heat exchangers and chemical reactors can be simulated with the COMSOL, and also how we can get the results and interpret that results for the better accuracy. So from the my bottom of heart, I say thank you to sir. Also, yeah, on behalf of Swedish College of Engineering, I would like to say thank you. And if possible, for this year, at the ending of this year in December, we are arranging one international conference in our college. So we invite you over there. Later on, we'll have email conversation with you, and we'll see in future that you will be in our campus.
Thank you so much. It's my honor, and I'm very happy to be here today and talking with you. I hope that you could have a successful life in your scientific life, in your personal life. And if there is any cooperation that we can do, it would be my honor, and I would be very happy. Thank you so much for everybody.
Thank you, sir. Thank you.
Thank
and
you.
With your permission, I declare that this session is over.
Okay, thank you so much.
Thank you.
Yes, have a good day, guy.
You too, sir.
Goodbye. Goodbye.
Bye.